Hello, everybody. This is Applied Mathematics at Northeastern State University. This is our video number 6. We're going to talk about chapter 7, which is the last chapter of the part 2, chapter 5, 6, and 7. This part talks about statistics and probability. So let's start from a joke again, okay? There are 3 types of people in mathematics: who can count and who cannot count. Got it? Now, today actually we're going to talk about a lot about counting, so it's actually a appropriate joke, I think. Okay, so let's start from sharing the whiteboard. So chapter 7 talks about probability. So what is the probability? Okay, you probably already have a lot of experience with it. For example, the weather forecast may tell you that tomorrow the probability of raining is like 30% or 40% or 50%. I never know what it means and what's the difference. And also, if you like to play board games, or some people like to gamble a little bit, you need to roll. There's a lot of probability involved in it, right? You roll a dice or something. You buy a lottery ticket, right? Again, there's a probability involved. So it's actually quite common in your everyday life to have this probability involved. Now, exactly when do we need probability? Okay, so actually we need probability for random event. So this random event is defined as you do something and you have several outcomes of this event, but you're not sure, you do not know which one is going to come out. For example, if you flip a coin, right, you could either get it like flip a coin. You could either get a tail or a hat, right? You do not know which one will come out. That's what we call random event. So it's unpredictable. Okay. Now, whether there is some underlying physics that actually can determine the outcome, we don't know. Just based on our experience, it seems like we cannot. And it's like there's like half of the time it come out with tail, half of the time it come out with hat. So, and that's the situation when we use probability, okay, to talk about things. It's actually a simplification for us. For things we don't know, we cannot predict. We just use this probability, and we normally say that there is equally probable to get tail or hat. And same thing, roll a die in a like 6-side die, right? A cube die, you get outcome 1 through 6. Again, this is a random event because we don't know what the outcome is, right? That's why we use it a lot in board games or gambling, right? We use dice a lot. Okay, so let's start from some really fundamental things. Okay, I'm gonna use basically a flip coins and roll dice as our 2 basic examples of talk about probability. Okay, let's start from the simplest case. Okay, let's say toss a coin. Okay, as I said, it is a random event, meaning that you either get a tail or a hat. Okay, so there's 2 outcomes, right? Now, because we don't know, we don't know what's going to happen, right? The simplest assumption we can use is there's 1/2 probability that you're gonna get we call it PT. Okay, P stands for probability. Okay, it's 1/2, and then there's another 1/2 probability we're gonna get hat. Okay, now this is a very simple case, right? You only have 2 outcomes, and you assume they have equal probability, so each one of them is 1/2. Okay, and but out of the simple case, we see there's some general features about probability. Firstly, to calculate the probability of getting something is like you specify a number of a specific outcome divided by the total number of outcomes. In this case, the total number of outcomes simply 2, right? Could either get tail or get hat. Now the number of specific outcome in this case is, if we want to calculate tail, which is 1, or hat is also 1. Okay? Now this formula assumes that all the outcomes are equally probable, which is the case for most of the cases we're interested in. But this is the general formula. Okay, this formula can be used to calculate the probability. Okay, another feature you'll see is if you take all the probabilities. In this case, you have this 1/2 for tail, 1/2 for hat. You add them together, you get exactly 1. Okay, and as it should be. This 1 tells you the probability of getting either a tail or a hat. It should be. It's always normalized to 1. Or you can say this is a 100%, right? You have to get something out of your toss, right? So this is actually a generic, simple but a generic feature of probability. Okay. Now, similarly, if you talk about roll a die, like a normal die. There's all kinds of dies you can have, but normally we have this cubic size, right? With dots on each side, each face, right? From 1 to 6. Again, the outcome you can have is 1, 2, 3, 4, 5, and 6. Now for each number, the probability to get each one of these numbers, there's only one possibility, right? To get 1. So the probability is simply 1/6. This is also 1/6. Okay, each one of this is 1/6. Again, the number of the specific outcome, which is you have, is always 1 divided by the total outcomes, which is 6. So you have 1/6 for all the probabilities you have. Okay. Okay. Next, let's consider a little bit more complicated situation. Let's say toss 2 coins. Okay. Or equivalent, you can toss 1 coin twice. Okay. Once, twice, it's the same thing. So when you toss 2 coins, your outcome of the 2 toss, right? Again, it could be either, see, in the first time, okay, first toss, you get either tail or hat, right? Now the second toss, same thing. You get either tail or hat. So together, the result of the 2 toss, right, could be either tail, tail, or tail, hat, or hat, tail, or hat, right? So you have 4 outcomes, right? Now use the same, totally 4. We can calculate the probability of each one of this outcome, right? See, out of the 4 configurations, there's only 1 case you get tail, tail, so it's 1 out of the 4 outcomes. So the probability getting this is 1/4. Now for tail, hat, right, and hat, tail, right, combine the probability. If you want to talk about the probability to get 1 tail and 1 hat, right, is you have 2 possible scenarios to get it, and then the total outcome is 4. So it's 2/4 or 1/2. Okay. Now for the case of 2 hats, right, again, there's only 1 possible case out of the 4, so it's 1/4 again. So these are the probabilities. Okay. Okay. Now another way to calculate this is to use something called multiplication principle. So what this says, suppose you want to calculate the probability to get 2 tails. Now you know in each toss there's a 1/2 probability to get a tail, right? sorry, this is 1/4. Now, the second toss, again, there's 1/2 probability to get a tail. So if you want to calculate the probability to get 2 tails, you multiply the 2 probability together, you got 1/4. And this is exactly the same as this 1/4. Okay. Now, similarly, you can calculate this case. If you toss the first case, it's possible to get a hat. Now, the second case is possible to get a hat. 1/2 probability to get a hat. So again, multiply 1/2 by 1/2, we got 1/4. Now, this case actually is a little bit tricky, but the same thing. Okay. Again, for this case, you have a tail and hat, right? You have to consider the 2 possible possibilities. The probability, the first toss, you have a tail, and then the second toss, you have a hat, right? And each one of these has probably 1/2. So it's 1/2 times 1/2 equals to 1/4. Well, the second possibility is you have a hat in the first toss, and then second case, you got a tail. Again, this is actually 1/2 probability times 1/2 probability, which is 1/4. Now, because these two both gives you a tail and a hat, so you need to add this probability together. So add them together, you get exactly. So 1/4 plus 1/4 is 1/2. Okay. So this part actually, there's related to this multiplication principle. And the second case, we actually use another principle called addition principle. Okay. Of probability. Okay. So what is multiplication principle? Okay. It says that basically, if you have an event that come out of a multi-event, okay, this event is a result of multi-event happening at the same time, then the probability of the end event is simply the probability of those multi-events multiplied together. So you have to have each one of these events happen so that the final event can happen. Like in this case, right? You have to have both. You have to have both of all of these happen, right? You have to have tail in the first case and tail in the second. So the probability of the first case times the probability of the second case give you 1/4. That's multiplication principle. Okay? Now, addition principle is if you have an event that can happen in alternative ways. Okay, there's more than one way to get one event. Then you add the probability together. Like in this case, right? You have 1/4 and 1/4. Both give you a hat and a tail. And this is 2 different ways, 2 different pathways to get the same outcome. So you add those probabilities to give you 1/2. So these 2 are actually already a little bit advanced concepts, but I think it's fairly easy to understand. Okay, let's also talk about rolling 2 dice. Roll 2 dice. Okay. The idea is very similar. So in the first roll, the outcome could be 1, 2, 3, 4, 5, and 6. Right. Now the second roll is the same, but it's a little bit complicated because each one of these, right, could have 6 result, right? You could roll second dice 1, 2, 3, 4, 5, 6. Similar here, you could roll 1, 2, 3, 4, 5, 6. Okay. Now you can write this on and on, but let's just I will just give you a demonstration here. So let's just write this too. Okay. Now outcome, right? 1 plus 1. So the result you get for total rolling 2 dice, you got number 2 here. In the second case, you have number 3, and then 4, 5, 6, 7. Okay. This is what you got out of the 2 rows combined. Okay. Now in this case, you have, okay, maybe let me use some commas to separate numbers. So in this case, you have a 3, 4, 5, 6, 7, 8. Now you can see the trend here, right? If you do this, you get you can start from 1. You get 4, 5, 6, 6, 7, 8, and 9, right? And so on. Okay. Now you can easily see that the total outcome, the numbers of outcomes here, right? Each one of these is 6, right? 6 times 6. So totally you have 36 outcomes, okay? And like, for example, if you want to calculate the probability of getting a 2 out of rolling the 2 dice, right? As you see here, right, there's only one case you got 2 out of 36 outcomes. So the probability of getting 2, let's call it P2 equals to 1 over 36. Now, similarly, you can calculate probability of getting 3, right? There's one 3 here, another 3 here. So the probability of getting 3 is 2 over 36, which is actually 1 over 18, okay? And you can do similar calculations for 4, probably getting 4 and 5 and 6. And actually, it turns out that the probability of getting 7 or 8 are the largest, simply because out of the oldest 36 outcomes, it is more possible. I mean, there's more outcomes corresponding to 7 and 8. And that actually, if you play board games, some of the board games, you notice that there's certain advantage of rolling. If you want to get the number 7 or 8 by rolling 2 dice is the best. I mean, you got most probability of getting those numbers. Okay. Now again, we could. This is the calculating those probability by basic definition. We could also use multiplicity principle like we did before, right? For example, to get 1 in the first case and 1 in the second case would be 1 over 6 times 1 over 6, right? Which is 1 over 36, and so on, right? Now, certainly, this kind of discussion can go forever, right? We can talk about toss of 3 coins or roll 3 dice, etc., right? The principle is the same, but the case get a little bit more complicated, okay? Now, these kind of tree diagrams, okay, are really useful for you to keep track of all the possible configurations. In the first scenario that you couldn't think about clearly about all the outcomes, just sit down and write out all this tree diagram. And then, although it's a little bit complicated, but it gives you pretty good intuition. So I actually recommend you guys do this, at least at the very beginning. Okay, now let's talk even a little more complicated situations. We can talk about all kinds of probabilities. For example, we can talk about probability of or, probability of not, and the probability of and. Okay, let me explain to you what I mean by that. Okay, let's consider again roll a single die. Okay, one question we can ask is, what is the probability to get either 4 or 5? Now, as we calculated already, the probability to get 4 is 1/6, and then probability to get 5 is 1/6. Okay. Now, what is the probability to get either 4 or 5? Okay, as probably some of you have felt about it, intuitively you just add these two probability together. So the probability to get 4 or 5 will be 3 or 6 or 1/3, and that certainly makes sense, right? Because you have totally 6 numbers, right? You won't get 2 numbers out of 6 numbers. You have basically 1/3 probability to get it. Okay. Another thing we can ask is probability to get something not 4. Okay. Again, this follows intuition, right? The probability of getting 4 is 1/6. So the probability of getting not 4 is simply 1 minus 1/6, where 1 is the total probability. So this gives you 5/6. So the probability to get not 4, or to not get 4, or not to get 4 is simply 5/6. Finally, let's talk about probability of and. Okay. Now, certainly, if you want to just talk about probability to get 4 and 5, it's just impossible, right? You never had this show out like 4 and 5, so this is 0. But there's a kind of and question you can ask. For example, you can get probability of not 4 and 5. Okay. Now in this case, how do you get it? Okay. Now as we know, the probability of getting not 4 is 5, 6. Well, the probability of getting 5 is 1, 6. Now, just out of your logic, right, you can see in this case, this total probability still equals the probability of getting 5, which is actually 1, 1, 6. So for this specific case, it follows this probability. Okay. Now, in general, when you have a question about probability of AND, you have to have both these two satisfied. Okay. Sometimes you could have some probability in some more complicated cases when both of them are satisfied. Okay. Now, in this case, you have to find out the overlap between these two probabilities, and then choose this as your probability. Okay. Now, in this case, the case of not 4 simply include the case of 5, right? So the total probability is simply equal to probability of 5. Of getting 5. Okay, that makes sense? Okay, in the end, let's consider a pretty complicated case of having probability. And you understand in this case, you're actually like a master. You're already like a master. Okay, so let's consider in playing cards. What is the probability of getting a queen or a club? Maybe let's talk about this, getting a queen and a club. Okay? That's probably, let's start from this. Okay, getting a queen and a club. Okay, now we take 52 cards, right? With 4 different colors, right? We have a club. Sorry, this is diamond. Okay, club. So spade. Okay, club, and then red heart. Each goes from 1 to 10. And then with a jack, queen, and king, right? So each one of these has 13 cards. Totally, we have 13 times 4, which is a 52. Okay, now what is the probability of getting a queen out of this 52 cards? Okay, certainly for each color, we have 1 queen, right? So we have 4 queens out of 52. So the probability of getting a queen is simply 4 divided by 15. Now, what is the probability to get a club? Okay, to get a club, you have 13 possible ways out of the 52. So the probability of getting this is the probability of getting a Q. Okay, to get a club, you have 13 divided by 52. Okay. Now because we have the N, right? So we're looking for a cross section between queen and club. Now certainly in this case, it's pretty simple because the only 1 queen is club. So that and this question is simply the overlap of this 2 group is just, there's just 1 possibility, right? Which is a club queen, right? And they certainly give you probably 1 over 52. Okay. Now, what do we want to ask about getting a probability of getting a queen or a club? That actually is the a little bit challenging question and was in the book. Okay. So how do we do this one? Okay. Now, as we see, as we said before, right? If there's no overlap between these two, right? We would just simply add them together, right? These 2 cases together. We will use 4 over 52 plus 13 over 52. But as we know, there is if we do that, right? We double counted 1 case, which is the case of this diamond, this club queen, right? So what we need to do is we add these 2 probabilities of the probability of getting a queen and the probability of getting a club. We have to subtract from it the 1 single case that we double counted, which is actually a club queen. So we subtract 1 over 52. Okay. So this is actually the probability of getting a queen or a club. Okay, so this give us 4 plus 13 is 17 minus 1 16. So 16 over 52 or 8 over 26. And then we could keep going, right? 4 over 13. That's the probability. Right? Does that make sense? Now, again, this is a little bit complicated, but you understand this example, you're a master in probability. Okay, let's talk about a very practical use application of this probability theory we just learned. We in general it's called expected value. And we'll consider a very practical situation of lottery expectations. Okay. Say, let's assume you have this following case. Okay, it takes you $1, very small amount of money, right, to buy a lottery ticket. Right. Now, as a result, the outcome could be like this. Okay, there is a odd of 1 in 5 or 1/5. Okay, 1/5 to get $1 back, a free ticket. So you like it buy free. Okay. Now an odd of a 1 out of 100 to get $5, and then an odd of a 1 out of 100,000 to get $1,000. Finally, an odd of 10 million, 1 out of 10 million to get $1 million. Okay. Now the question is, what is the expected value based on this outcome? Like if you spend your $1, how much money you expect to get back on average? So again, for this on average to work, you have to buy lottery tickets a lot of times. Okay, so on average you get this value, but this tells you a lesson about whether you should buy lottery ticket or not. Okay, certainly. Okay, see all these probabilities, if you add them together, it does not equal to 1, right? And that means for the rest of the case, certainly you do not get anything, right? So for the rest, you simply get $0. Right? You have to keep this in mind, right? Now, what is the on average? What is the return on each purchase? Okay, and how do you calculate that? Okay, you can simply calculate this by multiplying the money, the return you get in each case times the probability in each case. Okay, so you have, if you do this, you have $1 multiplied by 1/5, and then plus $5 multiplied by 1/100, and then $1,000 multiplied by 100,000, and then finally $1 million multiplied by 10 million. We actually should probably write it as scientific notation. Okay, the reason I'm writing like this give you some impression that it's a huge money. Sorry, this is multiplication. And finally, you have this $0 multiplied by whatever probability is left. Okay, certainly it doesn't matter what you have here; it is always 0. Okay, so this gives you the expected return of this purchase of a single ticket. Okay, now you can do this calculation, and you do it, you'll see that the return you have is actually going to be I'll just give you the answer. Okay, your return is going to be 0.36. Okay. So you pay $1, okay? On average, you got 0.36 back. That means out of the whole event, okay, on average, you lose 0.64 dollars, okay, on average. Each time you lose this money, okay? Now, to make it a little more make sense, I mean, you can put this as minus negative value because this is the money you pay out. Well, this is the money you get in. So -1 plus 0.36. So the total money you get is negative 0.64, okay? Notice that this is actually in the book, example 2 in section 7C. The book used a little bit different way to calculate it, but it's the same answer. And it's essentially the same. But I think this way of listing all the probabilities actually made more sense. Okay? So the take-home message here is, in general, it does not make sense to buy lottery, okay, ticket, because in general you have negative average return. Certainly in some really rare events, right? When you have some statistically speaking, a 5 sigma event or 6 sigma event, that you can actually get money, a huge amount of money. You can actually make this happen, right? That event is really small, so it wouldn't show up in this category. Okay? Now you must ask me, where does those odds come from? Okay, those odds actually you should be able to calculate them based on the rules of the lottery. Like if they say like whenever you have a 6, you win a certain amount of money, or whenever you have a combination of this or that, you have this amount of money. You can based on those rules to calculate those odds. Okay, now if the lottery is designed really well, okay, you should always expect yourself to lose money, okay? Because that's how they gain money, right? The lottery company or whatever, how they gain money is because you lose money to them. Okay. Now, occasionally, okay, they may screw up in terms of designing their odds, okay, so that if you calculate the odds, actually you got a number here that's larger than 1. That means if you put $1 in, you get $1 more than $1 back. In those cases, you can definitely take advantage and get a lot of money back. Actually, this happened in history. There was a philosopher in very long time ago. He's probably also a mathematician. He actually won a lot of money by taking advantage of a bad lottery design or whatever. Okay, that's just interesting to know. But this is probably not going to happen now. Anyway, this is interesting. I think this is an interesting example. Okay, and what we're calculating here is this 0.36 is called the expected value. Okay, in the end, to get your bonus point, answer the following question. Okay? Suppose you toss a coin, right? You toss it like 9 times, and amazingly, all 9 times you get a tail as the outcome. Now you're tossing it the 10th time, right? The question is, what is the probability in this 10th toss that you get a tail? Is that clear for you? Do you think it's still 1/2, or you think it's gonna be much smaller than 1/2 because all the 9 previous toss all give you tail, so somehow it should favor head more, right? This is a very practical question, right? As you play board games, sometimes you feel like you have bad luck, right? So you feel like this bad luck may be compensated later by some good luck or something, right? Does this really make sense based on our probability theory? Think about it and tell me your answer in your email. And that is all for today. And thank you for watching this video. I'll see you next time.